If you ask.
It has to figure out a way.
No.
Oh, hold on.
Oh, wait.
Can you hear me now?
Yes.
Oh yes,
There
there you go.
Oh
There
my
you
goodness! So I've been a ghost professor all this time.
Yes.
Oh, I'm so sorry. Well, I listen. You know, I do a recording of this lecture, so you can watch the link later. I'm so sorry. I didn't. One person finally raised their hand, and then Marin came on and said, "I can't hear you." Okay, good. All right.
Hey, it worked.
Isn't technology wonderful? When it works, we love it. Of course, when it doesn't, we're crazy. Okay, here we go. Let's go back to here. I guess it's comforting to hear my Southern accent. Okay, let's look at this problem again. We have TA at $4.05 per pound, and we have TB at $2.65 per pound. And then this is, say you work at Starbucks, it says blend 2 T's. Maybe your boss says, you know, Marin, I want you to produce a new blend for me. And I want 70 pounds of a tea to sell at $3.55 per pound. And then the manager says, well, do you know how much of each type of tea we have to use? And if you do it right, you get a promotion. So the thing is like, wow, I'll get a promotion. I'll make really lots of money kind of thing. But let's face it, ladies and gentlemen, college algebra is everywhere. So here's what I want you to do. I want you to write the concentrations, that is the dollars per pound in both cases, in all 3 cases as fractions, okay? And then set up an unknown, then we'll compare screens. Okay, so let's see how we compare. Now, here's what I've done. And like I asked you before, what we want to do is, again, do some symbolic computation. So we have X being the pounds of TA. I mean, it doesn't matter. You could do X pounds of TB. It would not matter. If your work is consistent, it makes no difference. So at least from that, this implies that 70 minus X will equal pounds of TB. So that part is easy. And again, you can use any letter that you like here. Now, as far as the concentrations, cash per pound, we have 3 of those. I simply write these with the denominator of 100, which essentially removes the decimals, okay? So again, just like the previous 2 problems where you had to read my lips, I guess what you're seeing here is that we're doing the same thing using the symbolic calculation. Ladies and gentlemen, I want you to be able to work with symbolic calculation because it will make you better. Now, let's do the Professor Ron approach. We're going to have TA and we're going to have TB. And then we're going to have the blend, that is the mixture. We'll just call this the blend. Now, these techniques I developed when I taught intermediate algebra the first year that I taught at San Jac North. And I've used these ever since because they turn out to be really useful. And I taught them how to do this symbolic arithmetic. So it's kind of stuck. So for TA, let's write down the concentration, and that's this one. So we have 405 over 100. For TB, let's write down the concentration. This is 265 over 100. And for the blend, let's write down the concentration. I've noticed that when I check the links, a lot of you do watch the lectures again, and that's good to pick up pointers and all. So I'm glad I have that for you. It's a nice device that we can record our lectures. Now let's just see here. What else do I need? Oh, now let's consider the amount of each. So here we have X pounds of A. We have 70 minus X pounds of B. And then of course we just have 70 of the blend. Now, when you look at this particular setup, this looks exactly like the last problem where we cleared denominators. In the previous problem, all the denominators were 200, right? So we multiplied by 200. Can anyone tell me what we're going to do to clear the denominators here? What do we multiply by?
100.
Absolutely. So write that in red. Now, this is what I talk about symbolic calculation. As we multiply by 100, the 100's absorb. You don't even have to write it out if you don't want. And then plus, again, multiplying by 100, this will absorb 265 times 70 minus X. And then, of course, the 100 here absorbs, and we have 355 times 70. Now, like I said before, I know that this is a little bit different, but now we're treating the numbers just like the variables. So we have 405x plus 265. Don't multiply, we just have what? We have 265 copies of 70. Then we have a negative 265x. And we have 355 copies of 70. Now, just like the last problem, you see this looks just like it. So what we want to do is put our X's together and get all our copies of 70 on one side, treating both of these like variables. So we'll have 405 minus 265 using the distributive law for the X's, putting this guy and this guy together. And now what we want to do is move this to the other side and factor it. So we'll have 70 times, I'll use a parenthesis here, 355 minus 265. So that way we know now how many copies of 70 we have. Now let's go ahead and do the arithmetic. This is easy arithmetic. 5 from 5, that's a 0. And then we've got 6 from 10, that's a 4. And then 2 from 3, that's a 1. So that's the only arithmetic we've had to do at this point, and that was easy. Now over here, let's do the same thing. So 5 from 5 is 0. And then we're going to have 6 from 5, or a 15 in this case, that would be a 9. And that's all that's left. So we have 140x equals 70 times 90. Now, you see we have common factors here. So I'm gonna do them one at a time. First, I'm gonna divide both sides by 10. So you can either divide this by 10 or this one, but not both. So I'll get 14x equals 7 times 90. You're thinking I could use a dot, but since I'm using the parentheses now, just remember when we divide by 10, since this is a product, we can only divide one of the factors by 10. So be careful, it's easy to make that mistake. And now we're thinking, all right, well, we're almost done here. We've got a 2 in the 90. So let's go ahead and write this as 7 times 2 times 45 because we're lazy. Now, you see, this is a 14 and this is a 14. So when we divide by 14, we're left with X. And somebody tell me when we divide this by 14, what do we have left? What happens when
Maybe a
we,
fraction.
Yeah, improper fraction.
yeah, but if we divide 7 times 2 times 45 by 14, this divide by 14, let me just write it out. And that gave us X, right? What do I get when I do this? What do I get? What's 7 times 2?
14.
What's 14 over 14?
1.
You just
Oh.
45.
Oh, there we go. It was so easy, it was difficult. You see what we did? Everybody, this is called symbolic arithmetic. This is what you do with X's and Y's, but you don't want to do it with numbers. So I'm trying to teach you how to do it with numbers. So when you do your physics and your engineering classes with Nate and also at the university, you'll be able to work with the numbers. That's a very important skill. You know, when you were younger, you worked with numbers all the time and then you left them behind. And I don't know why that happens. It's good to always do the numbers. Now, can somebody tell me now, what do I do with the 45? What does it mean? Let's look back.
Yeah, 70 minus 45 to find the pounds.
So, and who's speaking now? Is that Brian?
Noah.
Noah. What does this represent? 45.
Pounds of TA.
Yeah.
Yeah, pounds of TA. Okay, and so Noah, I think you told me how many pounds of TB do we have?
70 minus 45. Which is
Good. So 70 minus 45. What does that equal?
25.
25.
Yeah. So 25 pounds of what? TB. And I'll go ahead and summarize. 45 pounds of TA. All right. Now, again, what's important here is that the technique is always the same. When you've got concentrations, you're always going to get repetition of numbers. So use the numbers like algebraic quantities, just like we did in the first problem and especially the second problem. And you can see in this particular case that it all works out the same. Again, the symbolic arithmetic is going to make you more aware of the algebra and number theory that you have to do in calculus. Calculus requires you to work a lot with arithmetic, especially with limits, and a lot of really, really rigorous algebra when you do limit calculations, when you do differential calculations, and also when you get to Riemann sums to do the definite integral. So I'm trying to prepare you for that. I don't want you to get to your calculus and feel like, wow, I need to go back and review. I want you to be ready. Now, I'm glad you can hear me. I think that's really, you all were very patient. I think when Noah finally raised his hand and said, and then Marin came in and said, we can't hear you, you all both again get 10 points. Now, let's go back and share. When I say you get 10 points, that's a compliment. That says good work. If I say you get negative 10 points, that's not a compliment, but I don't do that. I just don't say anything. I'm a nice guy. I don't do that. So now let's go back to our share screen. Now, before we do the time, rate, distance, I want to do another mixture problem because this will kind of be just like what we did before. These tend to be kind of difficult for you. So I want to do this and then we'll back up and really do the crazy algebra and numbers for the time, rate, distance. So go ahead and look at this one. And let's just read it together. It says a car radiator contains 65% antifreeze. It says a suggested concentration for the summer is 50% antifreeze. The radiator has capacity of 3.9 liters. How much solution? Okay, so you're thinking we want to decrease the concentration of antifreeze. So the question says, how much solution should be drained and replaced with water to reduce the concentration? So this is really a useful topic. And lots of times when you take vehicles to be serviced, the mechanics and the auto technicians, maybe they got their certification from San Jack. If they did, you know, you'll have good work done. They will be considering this, and they will check their manuals and make sure that you have the right percentage of antifreeze in the particular vehicle that you own, because every car is different. And of course, you know, living in Texas, the summer heat is brutal on our vehicles. So this is a really relevant question. So what I want you to do with this problem first is just like the last one. I want you to convert all the percents to fractions and any decimal to fraction. And then also I want you to define the unknown, and then we'll compare screens. And like before, don't reduce anything. We like our unreduced fractions because it makes our life so much easier. So be wary of that. Okay, let's compare what we have. Now, again, this was a technique that I developed for my intermediate algebra students, again, to help them learn the technique, so they would have a particular procedure, just like you know, we talk about with the symbolic arithmetic in algebra. So first, we can go ahead and write the 65% as 65 over 100. We can write the 50% as 50 over 100. And then, of course, 3.9 is 39 over 10. Now, the unknown, that is, the problem says how much of the solution should be drained and replaced with water to decrease the concentration. And so we just let X be the volume of solution to be drained. That will automatically correspond to the amount of water to be added. So if you define your variable as the volume of water to be added, that would be fine too. It's not going to change anything. So what we're going to do is start out just like we had before. We're going to have a 65% antifreeze blank. And then, of course, the water is no antifreeze, and you're thinking, well, why do we bother? Well, we need to put this in so we don't forget it in the future. And then, of course, what is the goal percent? 50. This is the only time I'm going to write the percents. And again, ladies and gentlemen, these are not fraction bars. These are lines. These are blanks. And these are just labels. So now we're going to write the concentrations like we had before, 65 over 100. What number do we put in for 0%?
0.
Yeah, 0 over 100. That'll work, right? And
Yeah.
then 50 is 50 over 100. You're thinking we just put 0. Well, you know, that way if you're tutoring someone, they don't get mystified. Be consistent. Now, help me out. How much, once we remove part of the 65%, that's going to basically say, okay, how much do we have left of this? So we go over here and say, oh, we start with this much and we subtract X. This is the part that no one ever gets right. And then we're going to have X of this, though that's not going to have any impact on the equation. We actually, in this case, have X of this. And then over here, we just got what? What's the full tank? 39 over 10, right? So this represents the algebra, that is the word problems in an algebraic way. That is, we have to remove X liters of this solution. So that gives us 39 over 10 minus X. We're going to add X liters of water, which is 0% antifreeze. And the goal is 39 over 10 liters of 50% antifreeze. So now that's our equation. That's our setup. That's the hardest part. So just like we had before, if we look at this, what is the now again, when we might do this in 2 steps, but if you look at this particular problem, let's do it in 2 steps. We have these 100s on the outside, so we'll do this in 2 steps. Let's first multiply by 100, and then we'll hit it with a 10. That way, I think it'll be a little bit easier for you to see. So first multiply by 100, and these absorb. So we have 65, 39 over 10 minus X. Of course, that's 0, so we can ignore that. And then we get 50 times 39 over 10. And so I broke this up into 2 pieces, now multiply by 10. Just to break up the algebra so it's a little bit easier to see. So now what I want to do is what I taught you before. I'm not going to hit this with the 10. I'm going to hit the parentheses with the 10 to kill that 10. So that's going to be 65, 39 minus 10x. And then this will be 50 times 39. You're thinking, well, I could multiply the 50 by 10 and get 500, but I don't want to do that. I want to hit that number with the 10 to give me the 39. I don't want to hit the 65 with 10. I want to hit this part. I want to hit this factor with the 10 to clear the denominator. So note, denominator's cleared. And you can do it however you want, ladies and gentlemen, legally. Just make sure that whatever you do, that you're consistent so the denominators are cleared. Now you're like, wow, this is easier than the last problem. So let's go ahead and distribute. So we have 65 times 39 minus, in this particular case, we have 65 times a 10x. Now, again, when you do this, what you want to do is write this symbolically. Don't multiply it out, then we'll factor things. Now over here, we have 50 times 39, and then we'll do some little factor trees. Now notice, in order to get the positive coefficient for the x, just because we like that, let's take this term over here to give us 65 times 10x. And now we're going to subtract 50 copies of 39 from 65 copies. I'll go ahead and write it out. So that'll be 65 minus 50 times the 39. And I'm just overkilling the dots there, but I just want to make sure that you got that multiplied. So I'm emphasizing it. You can leave out the dot if you want, since I've got the parentheses. Now we're thinking, okay, what do we have moving here? Well, that's a 15, right? So this is a 15 times a 39. And now when we look, let's go ahead and look at the 65. Divide by 5, and that'll be a 13. Okay, well that's good. So we have 5 times 13 times a 10x. But now notice, if you like, the 39 has a factor of 13. So we have 15 times 3 times 13, because 39 is just 3 times 13, just doing a prime factorization. I'm not leaving anything to chance. I'm actually putting in more steps. So now you can see that this, in this particular case, let's see, oh, let me do this to make this a little bit clearer. Let me write the 15 as 5 times 3. No need to leave that. There we go, let's do that. Now, we can see that the 13's absorb, and the 5's do too, right? So they absorb, and we're left with 9 equals 10x. So we've reduced these unfortunate numbers down to something this simple just by symbolic calculation, by simply noting common factors with a factor tree. And now we divide by what? 10. So we get 9 over 10. So again, what I'm trying to emphasize here is a way to do the arithmetic and the algebra that allows you to utilize the power of algebra, because numbers and variables behave the same way, but you have forgotten that. And because you have forgotten that, your ability to work with the numbers in the algebra, I think, has weakened. So I want to build that back up. And so notice, just like with the previous problem, we can simply absorb common factors on either side of the equation, and then we're left with the relatively prime factors. And so now we see x is 9/10. So we go back up here and say, what does this imply? So this says remove 9/10 liter of 65% solution and add 9/10 liter of water. So again, the problem here that we see now, I'll go back up here where we started out. This is what I want you to review. This setup here. This is important. All of this is important too, but we're not solving the right equation or the right problem if we don't get this correct. So again, notice we're replacing part of the solution, 65% solution, with water, so that has no antifreeze component. So you have to really remind yourself of this so you don't put something over here that's incorrect. This is all percentages of antifreeze. And we have to make the correction here to show that we're removing this number of liters, X liters, from the 65% solution so we can obtain the 50% solution. And so as we move from the blanks to the equations, I did this in 2 steps. You could have hit this with 1,000, but I think that's a little bit much. It's kind of easier to see it in 2 steps. So as you work these problems, convert everything to these fractions and work it symbolically. And I think you're going to find that not only is your work more correct, but it looks better, in the sense that if you try to teach someone how to do these problems, they're going to be a whole lot more convinced of your ability if you can work it out than if you're sitting there punching on a calculating device and then they're like, well, I thought you knew how to do math. So trust me, we need our scientific calculators to get approximations that we need to push a problem for, like an awkward square root or the sine of pi over 12 radians, unless we use a identity from our book of tricks to write an exact number. There are times when approximations are extremely important, and I'm not downplaying that. But when we work problems where we are utilizing the algebra and the number theory, we need to be able to do this in a clean and efficient way, which we can see that we're able to do right here. Now let's go back and look at a time rate distance. So let me share my screen with the OneNote. So I'll pan back up here. Now, what I found about this problem, and I got this from your WebAssign, what I do that I think a lot of students don't always realize is that I choose these types of problems for your WebAssign homework. So your lecture actually helps you do your WebAssign and then helps you be better at doing your quizzes. You know, when you do your test, it'll be of a similar nature. So I want to give you techniques that help you with the homework. So I'm never going to, you know, waste your time. I'm always going to try to give you ideas that will help you get better. Now, here's what we want to do with this problem. And I think you'll notice that with the time rate distance, what is the method? Well, we know what the equation is for D equals RT, but I think in your past you may have done charts to organize particular parts of the trip, so to speak. And I'm gonna use that today to give you some ways to organize your thoughts. Lots of times you can fidget with the numbers and come up with an answer, but ladies and gentlemen, that's not the point of this. I'm not wanting you to fidget with the numbers so much as I want you to set up the algebra and get experience working with the algebra. That's the essential part here. I mean, you know, when you're taking a standardized test, you do it however to get to the next problem quickly. That's a completely different setup. So let's look at this particular problem. It says Wendy took a trip a distance of 330 miles. She traveled by bus and train, and we're assuming that she got from the bus to the train without lapse of time. So, you know, Superman type thing. The bus drove 30 miles per hour. So that was a nice leisurely drive on the bus to see the beautiful scenery. And the train speed was 65 miles per hour. Okay. Rates, great to know the rates. That helps us out. Then we're told that the trip time, here's another fraction, was 7.5 hours. Then the question is this: how long did Wendy spend on the train? So what part of that 7.5 hours was she actually on the train? Okay, so this is something that falls under the category of time rate distance. Now here's what I want you to do. I want you to convert any mixed numbers to fractions, and I want you to write a chart that has a bus and a train road, and then fill in time rate distance for each of those rows. So go ahead and think about that, and then we'll compare notes. And remember, D equals RT. Okay, I've written down some information, so let's go ahead and maybe you have done the same, and we'll go ahead and compare screens. Now, like I said before, I need a chart, and the only mixed number in this case was the 7 1/2. So we've already had some practice with this. This was kind of simple. That's just 15/2 hours. That's the trip time. Then I wrote the equation for the uniform velocity problems. Again, in calculus, you'll have variable velocities, and that will be something that you will use the derivative and integral to work. But for right now, we have, sometimes they call them uniform time rate distance. So D is equal to RT. So with this problem, since we have the trip time, we can divide by R and write T as D over R. Now, we know, again, the total distance, we know the trip distance, but we don't know the particular leg, so to speak. So I'm gonna let X be the distance for the bus. That was the distance that the bus actually traveled. Now, that just sets up the particulars for the chart. Now for your chart, and this is what I like about these problems, this kind of organization makes the work a lot more simple. And that way you don't forget what you're doing. So for the bus, we have time, rate, distance, likewise for the train. Now, in the given, we had that the rate for the bus was 30 miles per hour and the rate for the train was 65 miles per hour. And now I go over here and say the distance traveled by the bus is X, the total distance is 330. So this goes back to the mixture problems. The distance for the train will now be 330 minus X. So again, remember, all of these basic techniques we've used with the mixture problems, we can now use here, and it's not so bad. Now, to get the time, we go over here and we've got our equation. That is, for each leg of the journey, the time will be D divided by R. So we say X divided by 30. And here for the train, we have 330 minus X divided by 65. Now the numbers here aren't as nice. I mean, the numbers are not as compatible. So we're gonna have to do a lot of number theoretic calculations here to work this problem out symbolically, but that's good practice. So now this implies, again, we add the 2 times and that sum must be 15/2. So we have X over 30 plus 330. This is not even quadratic, but it's still formidable to solve with all the unfortunate numbers. 330 minus X divided by 65 equals 15/2. Now, when you do this, this would have been a really nice problem right here. This problem right here would have been a good problem for last week, but you would not have liked me. I thought, I see Dr. Stewart just saved this for time, rate, distance. So again, to solve this problem in a manner that's consistent with what we've done in the past is that we would want to clear denominator. So to the side, just say clear denominators. But what we're going to find is that the numbers aren't very user-friendly, but we can still survive the journey. So here's what we're going to do. We're going to do a little sidebar. This is what I always say when we need to do some side calculations. We're going to start with 30. We're going to do prime factorizations. This is 6 times 5. So this is 2 times 3 times 5. So we're doing what you did in general math, but maybe forgot, or maybe become rusty at doing. 65, we've already worked with this number. Again, this is 5 times a 13. Divide by 5, we get 1, and then we've got a 15. Divide by 5, that gives us a 13. So we've already dealt with 65. And then 2 is 2. 2 is a prime number, so we don't, it's its own factorization. Now, what we want to do is find the least common denominator. This is a technique you learned at one time, but again, I'm just reminding you what you do with the letters, which you're really good at doing. So now let's start with this one. We need a 2, a 3, and a 5 at least. So 2, 3, 5. So go up here and check these off. So far, we need one copy of each of these numbers. Now, when we go here, we're like, okay, we've got a 5. We just need one copy. We've got one copy there, so we're done with that. We don't have to repeat it. But 13, we don't have. So we need a 13. Wow. Didn't think we have all these numbers, so that gets a check. But now when we go to the 2, we have one copy of 2. That's done. So we call this the least common denominator. Now, again, you know how to do this. You do this with the variables, so there's no difference. What I found, however, is that when it's just numbers like this, everybody starts to falter. So now what we've done before is we multiplied the entire equation by the LCD to clear denominators. Now, what I'm going to do, don't multiply anything, leave everything factored. So we're going to have 2 times 3 times 5 times 13. Now, when you write this part of the equation, go ahead and factor the denominators like we have over here to make it easier to see. Again, this is the symbolic calculation. And then, of course, 65 is 5 times 13. This will serve you so well when you take calculus. Ability to work with numbers is an essential technique in calculus and in fractions. I mean, it is so important. I think everybody thinks calculus is just fun and exciting. It's fun and exciting when you do well on a test, but the work is not easy. The reward is doing well. That's when it's fun. I mean, it's a little bit different. So now, when we look here, we see the 2, the 3, and the 5 absorb. But what's left behind? We have an x and a 13. So we have 13x. Well, that came out really nice. There's not much left there. Now here, with the 330 minus x, we see the 5 and the 13 go away, but we're left with the 6. So we have plus 2 times 3. I'll write that factored for now, then I'll probably multiply it out. We get 330 minus x. So again, symbolic calculation, absorb, absorb, left behind. Now over here, we're kind of stuck. This is where all the numbers are, and that's going to cause us to do a little bit more work. Notice the 2's go away, but we have a 15, we have a 3, so we end up with 2 copies of 15 and a copy of 13. Okay, so symbolically, that's what's going on. So now let's go ahead and collect terms. So we'll hit these with 6's. So we have 13x plus 6 for now. We may have to go ahead and factor that later, times 330 minus 6 times the x. And that'll allow us to combine with the 13. So that was a good step. And over here, we've got, let's see here, we're going to probably end up factoring that. So I'm going to write this as 3 times 5 times 3 times 5. Just go ahead and prime factor that. Now, well, this is easy. 6x from 13x is 7x. And now what I'm going to do is I'm going to look at the 330 in a factor tree. So we can factor over here. So this will be 10 times what? 33. And that'll be 2 and a 5. And then, of course, a 3 and an 11. So that's good. And then, of course, we get a 2 and a 3 from that. So this will equal, we have 3 times 5 times 3 times 5 times 13 minus, now we have 2 times 3, that is the 2 times 3 there, and then these numbers here, times 2 times 5 times 3 times 11. So again, notice over here, 3 times 5, 3 times 5 times 13. And when we have the 6 times the 330, we have the 2, the 5, the 3 and the 11, and then the 2 times 3 from the 6. Now notice, let's just go ahead and compare to see what we have in common. We've got a 3, got a 3 there. We've got a 5, we have a 5. We have another 3, have another 3 here. We don't have another 5 over here, and we don't have a 13, so that takes care of all of that. So let's factor that. So we have a 3 times a 5 times a 3. And what's left behind is a 5 times a 13. Well, that's going to be a 65. We'll go ahead and multiply that out because we're going to need a difference here. And then here we have the 2, and the 11. So that's 4 times 11, which is 44. We need these numbers, so we need to write these out so we can get a difference. They don't have any factors in common, so it's okay to do that. We wanted to get rid of all of this because we had common factors. So now we have 7x equals 3 times 5 times 3. And now when we subtract, we get a 1 and a 2, a 21. So that's really good. The numbers aren't horrible because that gives us the 7 here. So now this is 3 times 5 times 3. Now write the 7 is 7 times 3. Now notice we got the 7 here and the 7 here, and we've solved the problem. If you divide by 7, you have x equals, so we've got 1, 2, 3, 3 times 3 times 3 times 5. Now, notice this is the value of x that goes here, and we need to know the time spent on the train. So we have to subtract that from 330. So let's just go ahead and figure out what this is. We can do the difference, and we don't want to factor that again. That we're fine with these numbers. These are easy numbers. So this is going to be 9 times a 15. So again, a 9 times a 5, that's a 45 with a 4, that's 135. So now we see that the distance the train travels is 135 miles. And so now the time on the train, so T, which is time on train, really nice problem now. We get 330 minus 135 divided by 65. But again, we get a nice number here. 5 from 10, that's a 5. And then we get 12, so that's a 9. And then, of course, 1 from the 2, because it's decreased, is a 195. But you can see this is just 3 times 65. We can easily see that. And symbolically, we get 3. So this implies Wendy spends 3 hours on the train. Now, what we're finding here with these types of problems, ladies and gentlemen, is the word problems in general are lengthy. So what I found is that when students take a test, the first test, they usually punt on the word problems in the sense of like, I'm not going to do the work on the word problems. I'm going to do the work on the lesser difficult problems and then, try the problems at the end for some pity points or whatever. What I would suggest with the word problems is spend quality time with these problems and make an effort to understand the symbolic arithmetic. That is, you can look at this problem here and now say this would have been a good equation from 1.5. And then you would say, oh, okay, I don't have to worry about this. I see that the solution is 3. Now, maybe you could sit there and fidget with it for a while and figure it out. But This is a college algebra problem right here. And this is what I teach. This is what I taught my intermediate algebra kids to do. At first, it was very odd for them, but once they figured out that the numbers were just like the variables, you can now see that utilizing the prime factorizations is kind of like saying x cubed is x times x times x. Or we say x cubed times y squared is x times x times x times y, putting the dots in. That's exactly what we're doing here. There's no difference. And while there seems to be resistance to doing this with numbers, is something we need to fix, because now you can see that you can work through numerically in a way that's going to make you better at doing algebra. So this is a good question. And when you look at the practice test and the SmartPen videos and all that, you'll see additional problems with time, rate, distance that again are similar, that use a chart. So you should practice on those, and then also do the other problems that you see in your WebAssign. Now, what I want to do is go back to our shared screen with the OneNote, and let's look at a fraction of work problem. I've saved this for last. And now you're going to throw rocks at me because you're thinking, why didn't you start with this? And you're doing all these difficult arithmetic problems, you know, and I agree. This way I get your attention, and then we can do a problem. What I did was I saved the fraction of work to last because the technique is easier and the arithmetic is trivial. So now when you do this problem, you're going to find this to be a walk in the park. So if you look here, we're going to do Bob and Jim fill a swimming pool. Then it says the job for both hoses is 18 hours. Okay, so this is a fraction of work. So if they use both hoses, they can fill the swimming pool in 18 hours. Then it says Bob's hose is 50% more efficient than Jim's hose. Okay, with that information, you should be able to compute the time for each hose to fill the pool alone. Now, these problems probably aren't as germane to what you're doing unless you are doing supply side economics and you're working with a manufacturing process and you're trying to make it efficient and you're trying to figure out, you know, how many people you need to work at certain times to optimize profit and things like that. So this might have some bearing, but again, given your work right now, the time, rate, distance, and the mixture problems are actually more germane to what you do in your other classes. But what I want you to do with this problem is I want you to write down a variable for an unknown that you don't know in this problem. And then I want you to think about how you set this up. That is, what is the time for Bob? What is the time for Jim? And how does that tell you the fraction of work per unit time? So go ahead and think about that. And then, of course, the 50%, you need to think of that, you know, in terms of a fraction when you actually write down the times required for each. So go ahead and think about that, then we'll compare notes. Again, this is a breather. This is a reward for all the hard work with the other problems. Okay, so like I found this when I taught this the first semester at San Jac, that the students were better at these. And in most cases, they used a technique that really they mimicked from the textbook. They didn't really understand my way until I taught it to them. So here's Professor Ron's way that you can teach to your friends, or if you become a student success tutor, you know, you can share this with your students. Now, what I've done here is that I've just assigned the variable T for the job time for Jim. So I say job in T, and that just means T hours. I don't put an H because I don't want it to be confusing. So Jim will take T hours for the job, T being the unknown. And then when you reciprocate that, you get 1 over T, part of the job per hour, fraction per unit time, fraction of the job per unit time. So you have to reciprocate. That's where you reciprocate, because these are like uniform motion problems. We're considering that their rates are uniform, that they're not varying, at least appreciably. And now Bob is 50% more efficient, so he can do the work in half the time. That's the 50% part that I was talking about. So Bob will require T over 2, all right? Or you could do Bob 2 and then make Jim 2T for twice as long. Either way, it doesn't matter. It's all consistent. And then, of course, as you reciprocate, you get 2 over T, fraction of the job, per hour. So now what we're seeing here is that the fraction of job per unit time times the amount of time that they work gives the fraction of the job, okay? So this is where my technique varies. I do the contribution for Bob, add it to the contribution for Jim, and that's the complete job, 100%. So this side is always a 1. So anytime you do the fraction of work problem, you might have 3 contributors over here. This side's always a 1 for 100%. So there's nothing to do here. This means 100%. This means job complete. That's why the fraction of work problems are so easy compared to the other ones. These are never as difficult. So if you utilize this technique here and this technique, then they go seamlessly and there's no issue at all. So now we have fraction of work per unit time for Bob is 2 over T. This is kind of like doing the mixture problems. And then the fraction of work per unit time for Bob is 1 over T. And they work together 18 hours times 18 times 18. So again, you're thinking, wow, why didn't we do this earlier? This is so easy. So now we get 2 times 18, that's 36 over T. And then of course 18 over T, and we have the common denominator. So again, this is very simple. That's why I saved this for the last word problem, and then we're going to start talking about inequalities. So again, 36 plus 18 is 54. Very simple arithmetic, divided by T equals 1. So reciprocate both sides, T equals 54. So what we see is Jim requires 54 hours for Jim. And then of course, half that, 54 over 2 equal 27 hours for Bob. So again, these problems compared to, I mean, you know, we think about all the arithmetic we have to do in the time, rate, distance where the numbers are unfortunate. Ladies and gentlemen, these numbers are unfortunate. When the common factors are so few and you have to do a least common denominator that turns into this number, these are what we call unfortunate numbers. They might as well all be relatively prime. I mean, really, these 3 numbers are relatively prime because there are no factors of 2 here. So these are what we call unfortunate numbers. Now, when we do this problem, we're thinking, why can't all problems be this easy? I mean, if I gave you this problem on a test, you'd say, thank you, can you give me 10 more of these and have them all count 10 points apiece? So the idea here is, now that you see a more elegant and efficient way to work with arithmetic and algebra, you can appreciate the fact that this problem, even though you need a technique, moves through very nicely. So again, relish the fact that when you do the fraction of work, you have much less arithmetic and algebra to do. So that's a good thing. All right, so when you do your 1.7, review the practice test, review the SmartPen videos, and review our lecture notes, and then work some more problems. Do as many word problems as you can stand. The more you do, the better you get. And then, of course, the more you help other people, the better you get. Now, what we want to do is say a little bit about some inequalities. When I say inequalities, I mean basic inequalities. Now, you did a lot of work with inequalities in college algebra. And so what I want to do is just give you some basic ideas. And then when we get to chapter 3, there'll be another section that will allow you to review these concepts. It really won't be anything new. It'll just be some problems that I'll throw in for you to do so you don't forget things. So this is what we call the basic inequalities. Basic inequalities. Now, there are two results. There's one having to do with how does an inequality work with multiplication by numbers less than 0, and how is the absolute value impacted by the inequality. So usually when you do equations, there's only one thing you have to remember about inequalities that's different, and that's pleasing, but lo and behold, everyone forgets it. So the first theorem is this. This is kind of like the zero product. So we suppose, and of course during office hours, if I don't prove certain results, you can always ask me about some of the details, and I'll be glad to share that with you. Suppose A is greater than B. That is, this is the notation that says that if we say A minus B, that's a positive quantity. That is, we don't know if A is positive or negative. We just know that it is larger than B, and that's what these symbols represent. And then we assume that C is less than 0. Now, what does that mean? Well, again, this means that C is negative. That's how we define a negative number. We say C is negative. And since the real numbers have really interesting properties when it comes to multiplying negative numbers, we can't avoid this. We have to talk about this. This also says, if you subtract B from both sides, that A minus B is a positive number. So when you actually do a proof of this, you actually have to utilize this fact and this fact. But again, it's not too difficult. But like I say, right now, I want to see this in action. Now, what's the result? Then this means if you multiply an inequality by a number less than 0, or division, same thing, division is multiplication. It reverses the sign of the inequality. So AC will be less than AB, excuse me, BC. Now, when you look at this, you say, I'll never forget this, Professor Ron. If I multiply by a number less than 0, divide by a number less than 0, the direction of the inequality reverses. So we'll just say inequality symbol reverses. So when we think about this, we're like, yeah, I got it. Well, what'll happen, you'll be doing a problem and you'll multiply an inequality by a variable that is actually less than 0 because you suppose that. And you don't switch or reverse the inequality. And then you wonder why the answer is incorrect or whatever. I'm saying that it's probably best to actually forget this a couple of times and then by your mistake actually remember it. So again, this has everything to do with the fact that if A is greater than B, A minus B is a positive number. And then if C is less than 0, then, and you may think about proving this on your own, then the additive inverse of C must be a positive number. So the real numbers are strange, my friends. We know that if we multiply a number less than 0 by a number less than 0, the result is a number greater than 0. That is a strange property of real numbers, which you learned in your college algebra class, well, actually learned in your Algebra 1 class in high school. So the real numbers are fairly strange when it comes to arithmetic, and we have to abide by that by using this result. Now, the next theorem is how does inequalities and the absolute value work together? So now we're going to suppose that C is a positive number. Okay, then, now we already have a result of an equality with the absolute value. I'll remind you of that, but we have the conjunction and the disjunction. Conjunction, and the next one will be the disjunction. Now, sometimes you see this in college algebra. When I do the pre-calgebra honors, I teach this, but this is not always taught. So, but this you use in calculus with limits. You can't get away from it. It's all over the place. So we would say that the absolute value of an expression, and we'll just denote that expression by the variable x, if it in absolute value is less than the positive number C, then the definition of absolute value actually forces x to be between C and its additive inverse. So the result here is that if you have this form, that is the absolute value of some real expression less than C, then you can write this expression. Now, of course, this has to make sense. I mean, you know, there are things that students always say, well, you know, this isn't doing exactly what I thought it would do. Well, I mean, you just have to abide by whatever's inside the absolute values. And you may get this. The thing is that not all inequalities have solutions. So if there's no solution, you just have to live with it. But if there is one, this moves to this. So we actually interpret the absolute value of a real expression less than some positive number as the compound inequality. So this is the compound inequality. So what's nice about this is that this is a convenient way to sandwich x between a number and its additive inverse. This is what we call a symmetric interval, about 0. And this is what you do in calculus. I can't get away from it. So you need to work a little bit with absolute value in this class, so you're not just astounded when you get to the definition of limit in calculus 1. Now, the other one is the disjunction, where we actually move this in the other direction. That is, we have the absolute value of x greater than C. This doesn't get as much use, but it's still important, this being the most important. The conjunction in use in calculus and analysis, you will see from here and evermore. So that is a very, very important result. Now this reminds us of the equality. That is, we get x greater than C or x less than the additive inverse of C, given that there is a solution. So here, this is joined, so to speak. Conjunction, together. This is separated, disjoint, separated. So we have x greater than C or x less than the additive inverse of C. So what's happening is that the inequalities are going away from each other. So though this is important, it doesn't get as much use as this. But again, we need to know. Now just recall that when we had the absolute value of X equals C, it looked like this. We'd either have X equals C or X equals the additive inverse of C, all right? So the idea here is when you think about this, you can think about this and remember it, but we don't have inequalities here, but you can see how these are kind of related, all right? So kind of tie this in with what we did with the equality with the absolute value. So let's do a couple of examples here to remind ourselves how we work with inequalities. And then I'll give you a boundary value technique. And then of course on Thursday, we'll do more inequalities. And then of course talk about our favorite topic, which is functions. The functions are the linchpin of what we do. And we'll get more of that, even though that might not be what you actually want to do. So for instance, say we have the absolute value of 5x plus 3 is less than 1/2. And we want to solve this in the real numbers. Now, what I want to point out here is that this is like using any formula, like in a science class or in a math class in identity. You have to make sure that the form is correct. So when we look at this, we see this form is preserved. That is, X has been replaced with 5x plus 3. So we have the absolute value of some expression, like we have here, less than some positive number, like we have here. So when we look at this, we say theorem, hypothesis. That is, what do we have to use it? Theorem hypothesis is satisfied. I mean, if we're going to use the quadratic formula, we have to make sure that we've written our equation with a 0 on one side, so we can write down a correct A, B, and C, because we derive that formula with that hypothesis. So if I want to use this result, I must have this, and we see that we do have that. So now what we can do, again, this is simple, but it's important. So we can now put the 5x plus 3 between the negative 1/2 and the positive 1/2 using the theorem, the conjunction. Right there. And so now, again, everybody thinks, well, okay, get rid of the fractions, multiply, but that's not quite what we're doing here. We're doing an inequality, and we want to isolate, if we can, X bounded by something below and above. So this is where we don't clear denominator, so to speak, because that'll take us backwards. So what we want to do is make an effort to isolate the X in between two real numbers. So to do that, let's go ahead and subtract 3 from everything. So I'm going to go ahead and write 3 with a denominator of 2. So that'll be 6/2, since I know I'm going to need to do that when I subtract from negative 1/2. So I get minus 6/2. And then I have 5x plus 3. I'll write out all the steps, even though I'm sure you can do it in your head, but we'll go ahead and write it out. 6/2. Well, let's start with the 1/2 first and then do the minus 6/2. So again, we've subtracted 3 from all of the expressions here in the compound inequality. So this will give us a negative 7/2. And of course, that's a 0, so 0 plus 5x is 5x. And then here, 1 minus the 6 is the negative 5. So now this is actually what we should have done. Now, in order to finish, we just have to divide by 5. So again, 5, if we go up here, 5 is not a negative number, so we don't have to worry about any reversing of the inequality. So I can just do like you used to do in your algebra class, divide by 5, divide by 5, divide by 5. Oh, note that we normally don't do this. Of course, if it were negative, then I would have to write a different inequality with everything reversed, or it wouldn't make any sense. because I need to abide by this. So again, we're starting kind of simple, but we will pick it up. So now this is reciprocate and multiply. So this will give us a -7/10 less than x, and then a -5/10. Now, of course, lots of times you'll say, well, you know, let's go ahead and reduce. Well, no, this is actually good, because now we see that x, and we've got magnitudes here, we've got x between -7/10 and -5/10. So WebAssign really is not going to care if you probably write that this way. If they do, just change it, but I don't think they will. So we can say x between, and this gives us a better idea of how the numbers are related. So if indeed the absolute value of 5x plus 3 is less than 1/2, then x must live in this particular interval. That is, these x's satisfy this. And of course, any x's outside the interval do not. So this is a way we can actually deal with absolute value and the inequality with the conjunction, okay? Now, the next example I want to do is just talk about a general technique, not necessarily absolute value, but a general technique for solving absolute values that has to do with sign understanding. Now, this particular example, you did these in college algebra, probably till you got tired of it. So we'll start with a simple example, then we'll bump it up some next lecture. So we have x squared greater than 4 times x plus 8. And we're asked to solve in the real numbers. Now, notice in this particular problem, we could try to do a case analysis, but that's really a little bit difficult here. And so we end up, you know, maybe we have a couple of inequalities that we need to solve. For instance, we could look at this and say, well, you know, if I go ahead and subtract this from both sides and get a 0 over here, can I maybe compare to 0 and, for instance, and figure out where the expression is positive? Would that be easier? And we say absolutely. So when we do this problem, we make a 0 by, again, moving this expression to the left-hand side. So this is a common technique when you're trying to solve non-trivial inequalities. If you have what we did in the last problem, we just have x to the first power. No problem. Move the x's around, move the numbers around, very easy. That is a very simple way to compute, because we have a handle on what's going on with first degree. But when we have higher degree, keeping track of the sign is a little bit more complicated. So now when we look at this, we're thinking, okay, maybe we can factor this. So let's go ahead and distribute x squared minus 4x. And this is just AC method, isn't it? I'm going to go ahead and do this. I mean, this is a -4 times an 8, but I'm just going to say plus 4 times a -8. I'm going to do it like AC just to kind of give you a heads up on this. So notice this is AC right here. If I put the negative with the 8, the -8 plus the 4 gives me -4. So this factors. That's my Z and that's my W. So this, we wish all of them were this easy. So now, equivalently, we have x plus 4 times x minus 8 is greater than 0. So now, when we look at this, we're thinking we have to compare this to 0. That is, when is this expression positive? Well, this is a quadratic, and you know that it is positive for infinitely many values. So first, you're thinking, okay, so how do I proceed? Well, a real expression can transition sign at zeros, and it can also transition sign for real numbers for which it is undefined. But notice this is always defined. There's no division by anything here that other than 1, which is not a problem. But now we can say, what are the boundary values? Well, -4 makes that 0, and +8 makes that 0. That's just the 0 product. And so now when you think about this, and this is a technique you used in college algebra, you can say, okay, well, I have an 8 here. Well, I tell you, after doing all that symbolic calculation, this is easy. I've set you up for simple now. You do those word problems with symbolic arithmetic, and you'll be set. Now, notice, we haven't done anything fancy here. Notice this has a leading coefficient of 1, so this will be large when x is large, and it will also be large when x becomes negatively infinite. So we can think about this like a polynomial. We can say positive here, then cross back into positive, because these are both multiplicity 1. And I'll say more about that later. So that's kind of a quick way to say, because this is multiplicity 1 and this 0 is multiplicity 1, the graph has to cross at those zeros. So this is indeed a transition point. -4 is a transition number for sign for this expression. So is 8. Now, if that doesn't ring a bell, or that's not something that you know is positive for you, no pun intended, we can say, okay, well, let's do this with just a little test point. We could say -10. We can use 0 and +10. So a test point is a point of your choosing, and then we want to check the sign. So we have x plus 4, just put the factored version right above the number line. And all we need to do is figure out the sign. So when we put in -10, this factor's negative, and this factor's negative, 2 negatives multiplied positive. So we already knew this would work, but we'll put a check there anyway. The graph told us that, but that was cheating, really. But we're still going to use that in the future because it's very useful. Now for 0, which is a number between -4 and 8, 0 here positive, 0 here negative, negative times the positive, overall negative, properties of real numbers, no good. Negative is less than 0. You want greater than 0. And while we're looking at it, if you note here, -4 makes this 0. So 0 is not bigger than 0, so that won't work either. Now, and again, of course, 8 won't work, will it? Because that makes that term 0. So 0, again, is not greater than 0. Now for the 10, we're thinking, okay, replace x with 10. That'll be a plus in the first factor. And 10 here, we get a 2. That'll be a plus. You don't really worry about the actual value, ladies and gentlemen. You just care about the sign. The value is of no use to you. I mean, unless you just want to compute it, but it's not needed. So this is a plus. So again, check. So now when you look at this problem here, you're thinking, well, follow the checks. If x is less than -4, and if x is greater than 8, this is true. So this implies, or if and only if, x element of, and you can use your interval notation because, you know, WebAssign likes it, -∞ to -4, union 8 to infinity. So again, what we find is that if the expressions get more complicated, that is, we get radicals or we get higher degree polynomials or fractions, then we have to work a lot harder. That is, we have to generate an equation that compares an expression to 0. And we can compare things to 0. Why? Because we can figure out boundary values. That is, zeros of the expression and also values or real numbers for which it's undefined, because those can indicate transition of sign. That's just a nice property of real functions or real expressions. So again, as you do more work, as we do more works to review polynomials, you can shortchange the work and use multiplicity of zeros to speed the process up. Or for right now, you can say, all right, well, that's good, but I like the test point because I can easily check the sign. So again, just remember, if something is greater than 0, that something must be positive. If something is less than 0, that something must be negative. Now, if we take this example and change it by 1 pen stroke, if we do this, greater than or equal to 4 times x plus 8, what you're going to see now is that the answer is exactly the same, but now we will include the -4 and the 8. Because when we run this down, we just copy this. This will just be x plus 4 times x minus 8 is greater than or equal to 0. Nothing changes here algebraically except the inequality. And so now, when we draw the number line, the -4 and the 8 work because we can have equal to 0. We get a check here, check, check, but of course an X in the middle. And X not meaning the variable X, just meaning no. Check meaning yes. And so now just by changing this, and we need to be careful when we're doing word problems, is it greater than or equal to? Do the words say that we need equal to? So keep that in mind. So now we can say x element of -infinity to -4 bracket union 8 bracket, again including 8 to infinity. Now this is minor. This is minor when we look at this, but when you're doing a problem, especially in calculus, you know, you're often interested in open intervals of upward concavity or open intervals of increasing. Including an endpoint doesn't change that. That is, one point's not going to be an interval of content. So student, I don't want you to get sloppy about it because most of the emphasis will be on open intervals. But when we add endpoints like this, this is basically just finishing off the problem. So we always need to be careful that we answer the question. Like if WebAssign says, you know, write the open intervals where the function is positive. It might be positive at the endpoint, but they said they just wanted the open intervals. So they just want these two. So the WebAssign might say, write all solutions to the equation that are real. And then it says separate them with commas. Now, if it doesn't say approximate, then you write exact. You write exact. So what's important, and this is what the WebAssign will train you to do, is to follow the directions and follow the formatting requests. I have not found any other software or textbooks, the Dr. Stewart Pre-Cal book and Dr. Larson's calculus book, that do a better job. The WebAssign can be frustrating, and it's like, oh, this computer's going to end up out the window. That's okay, because if you don't get frustrated, you're not working hard enough. Just remember, math is rewarding when you put in the time. So now, what I want you to do for next class is to go back and look at, you know, get a head start on the word problems. That is, go to 1.7 and start working the problems with the symbolic calculation. And then once you do some of those, I'll go ahead and put up the lecture video. Once you do that, and then of course you can practice reading lips. Wow, that's interesting. And then go ahead and look in section 1.8 at the preliminary work with the inequalities. And what we'll do on Thursday is that we will add some word problems that are actually solving inequalities, and then work into the function. So give yourself some time to reintroduce yourself to these types of techniques that we have with the word problems, and also to reintroduce the basic concepts with inequalities, okay? This has been a good lecture today. I appreciate your attendance, and I hope you all have a good rest of the day. Study plenty of math and exercise and get plenty of rest, and I think you'll be in good shape. You all have a good day.
You too, man.
Thanks.
Bye, thank you.
You all have a good one. Now remember what I always say, help your friends with math. Help your friends with math, because if you teach them techniques, you get better too, and it'll be a blessing for you as you study this course. So remember that when your friends send you an email at the end of the day, oh, I can't do my algebra, please help me. So be a kind person and help your friends, all right?
Got it.
Thank you.
Bye.